Peneplain's our speaker today. He's going to be talking about the Klamath Peneplain. I hope I pronounced that properly. As you can see from our schedule here, we have some time on during the month of March with spring break coming up. And then in April we have two talks. Jack Lewis is coming in and he's going to talk about the challenge of measuring sediment loads in streams and rivers. I think he's from the, what do they call that research place? The
Redwood Sciences.
I think that's where he's from, yeah. So he's going to come down. I'm looking forward to that. And then Steve Brown is giving a talk in late April on rapid prototyping of 3D models. And the talk is not going to be held in this room. It's going to be held over in AT in the AT 106, which is next to the CAD lab over across campus. And they do these things with computers, these models, and I'm really interested to learn about that. Anyhow, without any further ado, let's see. Hopefully yours is still right there, so you can start it back up again.
So I just click it?
Yeah, and then start it again.
Yeah, thank you. I need my glasses to see what I'm doing here. View show. Okay, you could get the lights. I'm a relative neophyte to PowerPoint, but I've been getting better and better, and it's fun to play with it. What I want to do is talk about the Klamath Peneplain, a term that was originally applied in the early 1900s by Joseph Silas Diller to an elevated flat-lying erosion surface. And this is the top of Thompson Peak, the highest peak in the Klamaths, and we're looking north-northwest. And when you drive 96 or 299, you see mountains all around you. But when you get to a certain elevation, and this is true of every non-volcanic mountain range in the world, we see a concordance of summits. This flat surface here, which tilts gently westward. And this is originally a lowland surface, which has been uplifted and the rivers have downcut into this surface, and that's what a peneplain is. Geomorphologists don't like using this word, and I never know why, but I use it, and so did Diller. So what I'm talking about is basically an article that I just published, the Klamath Peneplain, a review of the erosion surface, in this book, which has just come out, Geological Studies in the Klamath Mountains Province, the latest and the greatest on the Klamaths. The Klamaths are geologically the most complicated area of California, and if you want to spend $150, this is really worthwhile. You also get with the book a CD, which has a lot of mapping on it, which you can just look at or print out if you have a large format printer. So this is hot off the press. And the book honors William Porter Irwin, and I'll talk more about him in a minute. Now, to get the idea of the development of a peneplain, of course, the Klamaths are geologically very complicated. A lot of different rock units with different resistances to erosion. But if you go to the Colorado Plateau, where you have a lot of flat-lying sedimentary strata, you can get the idea of the development of an elevated erosion surface that we call a peneplain. Here we have Colorado Plateau, and we see a canyon. And the old Spanish explorers thought they could just go looking for El Dorado. Maybe El Dorado was up in the hills there, and they thought, we'll just cruise right across this landscape. But they encountered a little problem because you have these canyons with vertical walls that are over 1,000 feet deep, which they obviously couldn't cross. And here from an airplane, we see Lake Powell, which is filling up one of these, what we'd call entrenched meanders. We see a meandering pattern to the river, which carved the canyon. suggesting that, like the Mississippi, it was an old age river flowing on a flatland surface. Then about 5 million years ago, the Colorado Plateau, due to plate tectonic reasons, started elevating, and the rivers cut straight down. So you have these immensely deep canyons with the sort of entrenched meander form. Now, the same is true of the Klamaths. If you look at the Klamath River from an airplane, or the Trinity River, or the Salmon River, they have an entrenched meander pattern. But as I say, it's not so obvious because we have a lot of vegetation and a varied bedrock, which complicates the image, so to speak. If you look up in that canyon I was standing in, you can see the meandering pattern on the skyline 1,000 feet above you. Just don't be in that canyon if there's a rainstorm upstream. So Joseph Silas Diller did a tremendous amount of work in southern Cascadia, northern California, southern Oregon, the Cascade volcanics he did a lot of work on, and he did a lot of the original basic mapping of the Klamath Mountains and northern Sierra Nevada. Very, very good work, covering thousands of square miles, all done on horseback or muleback. And so he's the pioneer. And he was the one who recognized the Klamath Peneplain and wrote a very famous paper about it, which was published in a USGS bulletin in 1902. And he published a lot of 15-minute quadrangle maps, which were part of the USGS Folio series, which ran, well, they maintained it in the early part of the late 1800s and early 1900s. And so they produced a lot of basic maps, and here's one which includes Port Orford, just north of California in southwest Oregon. And he had these cross-sections, and it's in these cross-sections that he recognized the concordance of summits. And here's a photograph from his pioneer paper, The Topographic Development of the Klamath Mountains, from Barklow Mountain, east of Brookings in the Coast Ranges, and he would be discussing the concordance of summits. This is an old photograph. And in his paper, he talked about the evolution of the peneplain. So here are the pre-Miocene sediments, and then the younger sediments in the Klamaths. And he talked about the elevation of this surface and the entrenching of rivers into this surface. Now, he didn't know anything about the neotectonics of the area, the thrust faulting that we know about today. So the details, especially in the Coast Ranges, are off, basically. Age control is off, and the detailed story is not entirely correct. But the overall picture of the development of a peneplain during the Miocene, about maybe 10, 15 million years ago, and the subsequent uplift of this surface, he put that forth, and it basically has stood the test of time. Now, the next person of importance is Porter Irwin. And he sort of made his career, the Klamath Mountains. More detailed work incorporating plate tectonic ideas as time progressed. And there's Porter in typical field gear. He was a friend of HSU. He employed many of our former students as field assistants. And he's basically the most impressive field geologist I've ever met in my life. He mapped the entire Klamath Mountain province, a 15-minute quadrangle every 2 weeks in the 1950s and early 60s. And I've been in many areas. I've done mapping with him. And despite that rushed sort of progress of mapping, everywhere I'd go up a brush-laden creek, and everywhere Irwin said a contact existed, it existed, even with GPS, which he didn't have. He was always right on. He's still alive. He's pushing 90, and he doesn't go into the field anymore. This is a map of Cenozoic cover rocks in the Coast Ranges and Klamath Mountains that he put together So the older rocks aren't discriminated. The high-level erosion surface, the Klamath Peneplain, is shown in red. And so wherever we have these red patches, we have a gently westward tilting flat surface, which is Diller's Klamath Peneplain. Now we're going to focus in first on the area here east of Crescent City. And basically the data that Irwin used here came from a graduate student of mine, Linda Stone, who did a master's thesis looking at the Klamath Peneplain in the vicinity of Crescent City. And this is from her master's thesis. And what she's outlined here in this darker shade is the flat westward tilting erosion surface, the peneplain. Now up here in black, we have a young formation called the Weimar Formation, MWI. It's late Miocene. It's about 6 million to 5 million years old. And this line, XY, separates non-marine river deposits within the Weimar from a marine facies, mainly bay deposits going westward into open marine deposits, which are fossiliferous. They have diatoms, they have clams, and now from new diatom age dating, we know the age of the Weimar is this about 6 million years old, so late Miocene. So we see some patches here, and right now I have a graduate student, Caroline Lavenda, looking in detail at some of the patches of the Weimar down in this area. Now what's interesting is exposed along the coast at Crescent City is the St. George Formation, MSG, and it's coeval, the same age as the Weimar. It's basically a western extension of the Weimar Formation. It has a different name because it was mapped by different people in the early 1900s, and they just gave this name St. George after Point St. George. Here's Linda's cross-section along line B, and we see this westward tilted surface here, Weimar Ridge. There's a little patch of Weimar. And the Coast Range thrust, which separates the Klamaths and the Coast Ranges, is draped by the Weimar Formation. So we know the thrust faulting occurred before 6 million years ago. Standing up on that erosion surface looking eastward, we see the high Siskiyous, we see the concordant summits, and on some of these flat-topped ridges are little patches of Weimar Formation. And here we're looking westward, the ocean is in the distance, again concordant summits. And here's an unconformity which we found just the other year southeast of Crescent City, high up. This is Franciscan bedrock, Mesozoic in age, and here's a basal conglomerate of the Weimar Formation sitting on a fossil soil, a paleosol as we call it. And there's a little, if I can see it, there's a little worm tube burrow here, right there, yeah. And here's some Weimar. It's like ice cream on a table surface in the hot sun. The Weimar is just melting away. 100,000 years from now, there'll be no Weimar left. It's pretty weakly cemented sediments. And here we have intertonguing conglomerates, which are river deposits, and clay stones and sandstones, which have marine fossils. So we're right on the marine, non-marine transition zone. Here's some clay stone, some sandstone, and so this is probably tidal influence or estuarine. So you can get slack water, clay deposited, currents moving, sand deposited. And there's the fluvial facies. So this is a river deposit. And a lot of the boulders here are local derivation. They're from the Klamath basement rock. Now we'll look at the St. George Formation, which is pretty fascinating. And I did a tremendous amount of work on the Mesozoic Franciscan complex, which is shown in green and very well exposed along the sea cliffs at Crescent City headlands. But it's not the purpose of this talk to talk about the Franciscan. after I put in 25 years on the Franciscan, I got interested in the younger sedimentary rocks and mainly had graduate students work on them, and undergrads. Tom Leroy, who's here, worked in the Klamaths on some younger rocks. I had a fellow named Dane Robinson work on the St. George Formation, which is shown in this stipple pattern at Pebble Beach and north of Point St. George. And one of Harvey Kelsey's graduate students, Michael Polens, worked on the young Pleistocene terraces, and he found 3 different terraces. In black, about 100,000 year terrace. In number 2 here in brown, I don't have these numbers in the back of my head, but I think about 80,000, and this one in greenish yellow, about 50,000. So the story of Crescent City headlands has been uplifting of the coastline, and very, very recently these Pleistocene terraces, which are all marine, they grade to non-marine as you go east on the Crescent City plain, these have all just popped out of the ocean very recently. And normally you can't see it, but on a number of years ago, the sand was stripped away from Pebble Beach in July of, I think it was 1999. Sand moves around, goes here, goes there. And my student Dane had been looking at rocks up here and phoned me and said, "You ought to drive up there. It's amazing what's happened. You can actually see a lot of St. George." And by an amazing coincidence, I got to see things that he never saw just at the north end here, where we have 2 faults which he had identified on the north side of Point St. George, and a plunging syncline, and the faults tilt eastwards. And they came through, and I saw that they cut through the rock, the St. George Formation, and they folded the St. George into an anticline-syncline pair, which has since been covered by sand, and I may never see it again. It's just under the sand. And the other thing we found is this fault cut right through the St. George, and it transported some Holocene bog deposits, freshwater bog deposits, over St. George. So this is a very, very young fault. We got a radiocarbon date on those bog deposits. So these are the northernmost onshore active faults in California, which Dane and I found. So here's Dane's stratigraphic generalized column for the St. George. We have a soil developed on the Franciscan complex, and then we have high energy marine deposits grading upwards into muds with a lot of clams, both scattered and in storm shell accumulations. So basically finding upwards, then an unconformity, and then the Pleistocene terraces. But what's fascinating is Dane found a 6 million year old forest rooted into the Franciscan. And what he concluded is the forest was destroyed by a giant tsunami, which knocked over the trees. And here's the unconformity. This is a soil developed on the Franciscan. That's seawater with bubbles. And here's the basal St. George, and look at all that woody debris. Those are spruce logs, which are somewhat carbonized, but they burn if you dry them out. And here's a rooted stump, which is normally underwater. This is at extreme low tide, the low tides you get in the summer solstice. And this, there's a 6-inch scale, and this stump is rooted into the Franciscan, and it's buried by a fossiliferous St. George, which contains a lot of large logs, some of which are maybe 10 meters long, and they're all pointed the same direction. So that was a fascinating find.
Logs are 6 million years old.
Yes, the diatoms. We were so excited about this, we got John Barron, who's a diatom specialist in USGS. He was willing to look at diatoms from the St. George every meter through 40 meters of section. So we have very, very good age control on this devastated forest. based on diatoms. Here at Pebble Beach, there's a log. This is all under sand now. If you go up there, you're not going to see it. At wintertime. And here's this plunging syncline. This is in St. George. The beds are dipping in towards the staff. And then there's a fault, and then there's an anticline, a very gentle anticline. And that's all. I'll probably never see it again. It's there. And here's one of the young faults. We've dug out the fault plane on the north side of Point St. George Formation, and it's overthrusting the 50,000-year-old terrace sediments. And then at Pebble Beach, we have this 3,000-year-old bog deposit, and there's another big fault running through here, and the bog deposit is sitting on St. George, which is thrusting over St. George. And we convinced a paleobotanist, Diane Irwin of Berkeley, to come up, and she was very excited about the bog deposit because she said it's rare you find preserved spruce cones of this degree of preservation. So she did the radiocarbon for us. So we wrote this all up for California Geology, which unfortunately was subject to state budget cuts, but our story was published in May, June 2001. So here's the uppermost St. George, and here's a young terrace deposit sitting in angular unconformity on top. So let's extend the story down. I've turned Porter Irwin's map sideways, and all of you, I'm sure, know about the Wildcat Group. You've probably all taken field trips to look at the Wildcat Group. And I want to talk about the Basal Wildcat Group, exposed at Centerville Beach and Scotia and on Palco land inland, because it's exactly the same age as the Weimar and the St. George. So it's part of the story. So here's the Eel River Valley, and here's the general section of the Wildcat Group. About 3,000 feet of section, some nice ashes giving age control. And the basal unit is the Pollen Formation, which is very, very well exposed at Scotia in the river bottom. And we know from Arco propriety seismic lines, which Giovanni Vaduro has worked on, that the Wildcat Group is in a sort of large synclinorium. And when we look at the marine portion of the Wildcat Group, it retains pretty much a constant thickness under the Eel River Valley and up at Table Bluffs on the other side. So originally, the Wildcat Group was a blanket of shelf sediments which covered the coast ranges, all the way down to Garberville and all the way up to the Weimar. The Weimar is part of the Wildcat Group, in essence. And as the Mendocino Triple Junction migrated northwards, the Wildcat Group rocks have gotten deformed and uplifted. And so what we're looking at is a large syncline. Well, it's complicated by internal faults and folds, but basically a large syncline across the Eel River Valley of what originally was flat-lying, constant thickness, pretty much, sediments which have gotten warped into this synclinal form. And this is very important because other than myself and my graduate students, no matter who else you read, in articles that were published way back when and on until last year, everybody says the Eel River Basin was a subsiding trough during deposition of the Wildcat Group. And for years we've been telling them, we started in 1991, saying this is ridiculous. It's not true. All we're looking at in the onshore area is a big fold which developed as the Mendocino Triple Junction migrated northwards. There was not differential subsidence in the center of the Eel River Basin during accumulation of the marine portion of the Wildcat Group. Now, another thing that we've discovered, which is contrary to a lot of other people's point of view, if I can find the cursor, there it is the Pollen Formation. What we started out is Franciscan equivalent rocks of the Yager complex. This you see at Scotia, highly folded deformed rocks, lower Cenozoic, maybe 40 million years old in age. They were beveled into a wave-cut platform prior to the deposition of the Basal Wildcat group. And the Basal Wildcat group is shallow marine. And we're the only people who say that, and we know it. And so we keep on trying to educate the rest of the scientific world. And what happened is this Basal Wildcat group was deposited, the Pollen, and by the time you get to the Eel River Formation, the water depth was several kilometers, based on many different paleontologic microfossil studies. So the bottom fell out of the world. And I don't know why. I've talked to Tanya Atwater about this, considered the magnetic anomaly pattern on the other side of the Gorda Rise. I don't know why it happened, but all I know is the history of this unit started out a wave-cut platform, near-shore marine sediments, and then for whatever reason the leading edge of North America at this latitude started subsiding at a fantastic clip. I'm not going to get into that. William Miller, our paleontologist, and I have a paper in the mill about the Wildcat group at the Basal Wildcat group at Scotia. The section has gotten very well exposed because last winter there was a big landslide and it diverted the river and cleaned off the rock. If you haven't been down there, it's an amazing sight, what you can see now as compared to what we used to see. So here's the abrasion platform on folded Yager complex. We start out with a muddy breccia, and then we get bioturbated sands, then breccia with grading, and then bioturbation. And then we have some trace fossil concentrations. And as we go up section, that's a 2-meter bar, it gets muddier and muddier. So that's what it's like. Here we see from an airplane the Eel River Valley in the distance, and this is Franciscan Rock, and here's the Wildcat group at Centerville Beach, all tilted northwards. Table Bluffs in the distance where it's tilted southwards. And here at Scotia we see this very important cleaned off outcrop. And this was never exposed so well until last spring. So here's the unconformity at the base, and I know the picture doesn't do it justice, but these are Franciscan rocks. The Wildcat group is tilted about 80 degrees north here, so it's up on end. And here's the basal breccia, very poorly sorted. And the clasts within the breccia are mainly entirely pieces of the underlying basement rock, and they're quite angular. And here again, very crude stratification. I've rotated all the slides so that up is up. So if the perspective looks a little weird, that's why. But it's simpler to make up. And what William and I think are these are debris flows that came off sea cliffs out onto a nearshore marine abrasion platform. And we have a good analog for that just south near Punta Gorda, the Lost Coast. In the wintertime, these drainages suffer catastrophic mass failure, and you get debris flows rocketing out into the ocean. And so these uplifted terraces south of Punta Gorda are made from a very poorly sorted debris flow deposits interstratified with sandy beach deposits. And this is an exact analog for what was happening at Scotia 6 million years ago when the Basal Wildcat group was deposited. So we go up section, we get more debris flow deposits. Here's a clast which prior to incorporation into the debris flow was bioturbated. There are borings in it. These are marine fossil or marine organism produced borings, so they're not from the Eel River or any biota in the Eel River. And then this is from our paper, which is in the mill. And I'm no trace fossil specialist, so I'm not going to inundate you the way William would with 50 Latin names. Whenever I'm in the field with him, he's over there lying on his stomach staring at one little patch of rock for 2 hours. And if you go near him, you think he's giving a speech in Latin. I have no idea what he's... But He's one of the world experts on trace fossils. And he basically concluded that the trace fossils in these sandstones are shallow marine. They cannot be deep marine. And there are these vertical types here, which are Rossilia socialis, and they're found in the modern world in nearshore marine sands. They're not found in deep marine sands. And while there's a lot of sedimentologic evidence suggesting that these are shallow marine deposits, it's really the paleontologic evidence which is the nail in the coffin, so to speak. And when we publish this paper, I'll send it to my nemesis at the USGS, who did her dissertation on this section and insisted the basal deposits were deep marine because it fit her preconceived model. The worst example of science I've ever seen, where the model dictates what you see. Nonetheless, she got a PhD for it at Stanford. We don't talk when we go to meetings. There was a meeting at Menlo Park where we talked about the triple junction, and she gave her story, and I got up after, and I said, well, I hate to say I have to disagree 100% with everything the previous speaker said, so we don't talk anymore. So anyway, more of the trace fossil stuff, which I can't knowledgeably talk about. Again, more trace fossils. Well, this paper will be out. And then when you go up section, you get eventually near the railroad tracks, the Rio Del Formation, which is outer shelf to inner shelf deposits, and then the Scotia Bluff sandstone, which are beach deposits. So, and then here at the beach, a volcanic ash in the Rio Del Formation, and here we have the Scotia Bluffs going up into the Carlotta, nearshore marine, and eventually fluvial deposits. I'm sure a lot of you have looked at these. Well, another student, grad student of mine, Kathy Moley, did her master's on the sandstone composition in the Wildcat group, and I did work on the St. George Formation. And basically what we found in both of the units was there was too much potassium felspar to be accounted for by local derivation from either the Klamath Mountains or the Coast Ranges. And here's a diagram. K is potassium felspar, and you see in the Wildcat a lot of points tending towards K. There's no potassium felspar in the Franciscan complex. And so we got suspicious about the story. Everybody said that the Wildcat group was derived from the Klamaths or Coast Ranges. And we got suspicious of that. And her work suggested there was a more complicated story. And we can tell potassium felspar if you make a thin section and you stain it chemically for plagioclase and potassium felspar turns yellow, and so it's very recognizable. This is a 100-power magnification of a sandstone under a microscope. The field of view is about 1.5 millimeters across. So she and I did a lot of work on different formations looking at this. But then I managed to convince some Berkeley people, Paul Rennie and Warren Sharp, and then eventually a person, Sam Lanningham of Oregon State at Corvallis, were willing to look at micas within these formations, and they have a tool called argon-argon dating. And it gives you the very, very best radiometric age date that you can get. And so we did the dating, and what we found in the marine portion of the Wildcat group, going on up into the Scotia Bluffs Formation, so way up section, we found age dates on micas, 50 to 65, 70 million years. And the ones that I have a red bar next to have no source in either the Klamath Mountains, Coast Ranges, or Sierra Nevada. Now the Berkeley folks have looked at intrusions through the entire Cordillera, western mountain ranges of the United States and Canada. And they have the ages pinned down. And opposite the red bars, the ages indicate without a doubt, according to them, and they're the specialists, derivation from the Idaho batholith. So the sands within the wildcat group, maybe not all the sand, but a good part of it, has an Idaho signature. And the argon-argon dating is a very, very certain. And so we published this, and the paper in this latest volume includes this data from the St. George. And beyond the shadow of a doubt, we know that the St. George and probably the Weimar and the Basal wildcat going all the way up into the Pleistocene wildcat, all the marine portion of the wildcat, had some sediment coming all the way from Idaho. And that fits the picture because the Klamaths were a lowland surface. And so there were river systems that managed to transport sands from Idaho all the way to our neck of the woods. And from a paper that I wrote with Linda Stone and Kathy Moley in 1995, we had a model where we start off in the late, in the Pliocene with the Yager terrain, and we have a shoreline somewhere to the east, and here we have the Pollen Formation, and then up at Crescent City we have the Weimar and St. George Formation, and as you go east we had river systems, some of which must have come all the way from Idaho. We call it the ancestral Snake River, just to say something poetical. And then by the late Pliocene, about 2 million years ago, we had accumulated a shelf sediment blanket, which incorporates the wildcat group. And we feel that shelf sediment blanket extended and included the Weimar and St. George formations. So we envisioned a very low relief landscape to the east and a thick accumulation of shelf sediments just accumulating all through the late Miocene and Pliocene and early Pleistocene. And then the tectonics began. Already the leading edge of North America had, for whatever reason, subsided a great amount to allow space for accumulation of all this sediment. But then the triple junction here between the Pacific, Gorda, and American plates migrated up into our region. And we had these tremendous tectonic forces operating, which were translating the Sierra Nevada block northwards. And we had subduction of very young oceanic lithosphere underneath North America, opposite to Oregon and Washington and northernmost California. And what we were doing is shoving young sediment down the tubes and underplating it under the Klamaths, which caused the Klamaths to start rising up. And so this began in the Pleistocene. And we think the uplift of the Klamath Mountain block is a Pleistocene event, which disagrees with everything everyone else says. But we know we're right. So we go back, I'm almost done here, to Linda's great map, and I tried to put in the non-marine in green, marine, I couldn't make it tilt, in blue, Weimar Formation sitting on top of her erosion surface. And so all this was down below sea level, and maybe there was some 1,000 meters of sediment on top of this. And then in the Pleistocene, the Klamath started rising, and just as I said, as ice cream on a table in the hot sun, the Weimar just started melting off the landscape. And we just have these little, very delicate patches left, sitting way high up, thousands of feet above sea level, on top of Diller's classic erosion surface. And the uplift continues. That's it. Yes.
Is there any evidence that there's a paleo drainage system that you could extend from coast ranges to Idaho?
No, and when we published our initial thoughts on this, it upset a lot of people who were trying to envision where the sediment would have come through the old Cascade volcanic rocks. We know the Cascades were developing as a chain of volcanoes, I think as long ago as 15 million years. Maybe someone knows the old. And so they were there. But today, the Columbia River flows through the chain. Now you might say, well, maybe the sediment came from Idaho down some Columbia drainage and then by longshore transport south. But that's not possible to account for the case bar, the potassium feldspar, that way, because from modern experimental studies, it doesn't survive that amount of fluvial transport or longshore transport. And also the micas, they're too fragile to have made that journey. They could make it down a river, but once you get into the surf zone and longshore transport, they'd be destroyed. So we stick with our story, which ties ultimately in with Diller's 1902 story, that it was a lowland surface. What he didn't know, which we feel, is how recently it's been uplifted. And as I say, this paper, summary paper, has just been published, and I'm waiting for feedback.
Any other questions for Ken?
Yeah.
So, going back to the peneplain here, what do you envision as potential future research projects to continue to investigate the peneplain? What are the big primary unanswered questions or mapping that needs to be done?
There are techniques, fission track analysis and this sort of thing, which a team sort of led by Mark Brandon of Yale University has been working on, looking at uplift of the peneplains and the Colorado Rockies. And I've spoken with him at meetings. I know him quite well. And he's interested in the Klamaths. And these techniques are using a lot of very expensive instrumentation. And there's some potential of getting a better handle on the story. There are little patches of Cenozoic sediments sitting high up on the erosion surface in southeastern Oregon in the, the Kamloops wilderness area. And I've never seen those. And I've tried to get some students who don't mind a lot of hiking and backpacking to go and take a look at those. That's something that should be looked at. Porter hasn't seen them either. He just got the locations off old 1930s USGS mining reports. Because there's been a lot of gold mining. Every time you find these Cenozoic cover rocks, as you know from your senior thesis, you find evidence of a lot of hydraulic mining back in the early 1900s, because the deposits do contain placer gold. Linda was basically looking at placer gold mines. She found outcrops which had been hydraulically mined.
Any other questions? Does the Weimar Formation show the same signature?
Well, that's part of the story. I think the failure is sort of upper wildcat equivalent. And no one's looked at the sandstone petrology, and no one's tried to separate micas from it. So there's more that could be done. There could be more systematic sampling. But the trouble is you have to convince the Berkeley crowd or someone else to do the argon-argon dating. And that's very, very expensive. So you have to get them interested, because if you're like me, you don't have any money, grant money.
Is the top of the Weimar exposed anywhere?
Well, who knows what the top was? There may have been several thousand feet of section there originally.
So what's the thickest section that's exposed?
Well, the thickest section is basically the St. George Formation. Dane measured about 40 meters of section at Pebble Beach, and the top is an erosional unconformity, so who knows how much section there originally was. So we're just grasping at little bits and pieces, remnants of what's left.